Hello guys, I'm back. So last time we went over a simple linear regression model, right? So essentially what we wanted to do is we wanted to measure the relationship between wages and schooling, right? And it was specifically an OLS regression model, right? So the goal of the model was to estimate some of the fundamental parameters of the model. In this case, our primary interest of that model was to generate beta 1 hat, right? Which is essentially the OLS estimated slope. And also along the way, we generated beta naught hat, right? Which was these two sort of calibrated our prediction line, right? So the goal was to essentially minimize what's called the sum of the squared residuals, right? And the way we went about that is we calibrated a regression line, right? We calibrated a regression line that was essentially centered, right, around the distribution of the unobservables, right? So essentially, given that, we came up with, this is just a recap, we came up with about two assumptions, right, in order to enforce the validity of the argument, right, which was a zero conditional mean assumption, which was essentially that the expected value of the unobservables, right, given schooling was 0, which was also equal to the expected value of the unobservables, right? So these were our main assumptions of the model, right? And then essentially they assumed that some of the unobservables, which aren't represented in this model, just an example, luck would be an example of something unobservable. We're saying that the average luck, or the expected value of luck, is essentially the same across groups, across our explanatory variable, right? And so we're saying that essentially that accounted for the unobservable is via the zero conditional mean, right? The problem is that's not very realistic. It's not very realistic because typically there's a whole bunch of other what's called confounding factors that would distort the relationship between schooling, the exact relationship between schooling and wages, right? And make our causal inferences that we want to develop less plausible, right? So what I mean by this is there are a bunch of factors that could be useful and could be set up along this regression, along this model, right? But they're stuck in that unobservable, right? They're stuck in the unobservables, right? And they also, one of the confounding factors could potentially be correlated with schooling or wages in a way that could harm the validity of this model, right? And so we want to make the unobservables truly unobservable, right? And so the way we do that is we remove some of the confounding factors from the unobservable group and plant it into the model, right? To, like I said, to reinforce the validity of the zero conditional mean assumption, right? And the way we do that is essentially we want to develop what's called a multiple linear regression model that takes into account multiple factors, not just schooling, right? Because it's obviously there are more factors. There are more factors that influences wages than schooling in reality. I mean, that's sort of implied. So we have more factors, like for example, X2 could be high school GPA. You could also put potentially the school that you went to, connections, et cetera, that would essentially, like I said, reinforce the validity of the model, right? So this is where the multiple linear regression comes from, and we'll be developing a whole new set of assumptions based on, well, not really a whole, there's some similar assumptions in there, but we want to develop some new assumptions based off of that framework and work from there. And there are a bunch of implications to this that we'll get into, but that's explanation for it. Okay, so essentially, to recap, right? Like I said, if we do not remove some of the confounding factors from the error term, then essentially we are prone to overestimating some of our key fundamental parameters of the model, right? So we're prone to overestimating beta 1 hat if we also capture where you like college, where you went to college. That's just an example, right? So as a result, we develop a multiple regression model where we basically take the effect of one explanatory variable on wage, holding or controlling for other explanatory variables. Now, what I want to bring up now is one of the fundamental differences between a simple regression model and a multiple regression model in OLS is that in a simple, right, if you recall from the last video I made, we came up with an OLS estimator of beta 1, which was basically, in short, this is the covariance of X and Y, which essentially measures the collinear dependence of X and Y, right, over its sample variance, right, over the covariance of X, which is the way X moves, right? It's just the variance of X. I don't know what I was talking about there. This is essentially the OLS estimator, but, right, in multiple, it's a little bit more complicated, right? So, in simple, we only had one explanatory variable. In multiple, we have many explanatory variables, right? So essentially, the problem is, if we were to decompose for example, if we were to decompose one of the explanatory variables, right? If we perform a decomposition, we essentially have a portion of the explanatory variables that co-move, or that explain changes in wages, right? But also that they co-move with other explanatory variables, right? So this is a bad source of the explanation, right? But essentially what we want to do is we want to isolate the portion of the explanatory variable that doesn't co-move with the other explanatory variables, right? And also has a relationship with wages, right? This is the good source, right, that we want, right? So we want to estimate that. And so essentially that leads us to come up to the conclusion that the OLS estimation of the slope parameter, right, is equal to essentially the residual, the estimated residual of the explanatory variable. J is just, we have many explanatory variables, so this is just to basically say, oh, for J number of explanatory variables. But anyways, we have the portion that doesn't co-move with other variables times Y, all right, over the portion that again doesn't move the other explanatory variables squared, right? But this is kind of similar because essentially this is just the same thing as this, right? Because we have, this is just what I just erased it, but it's really the same thing, right? We have a y over here, a y over here, right? And this is the portion that doesn't move. This is the portion of the explanatory variable that doesn't co-move, right? But it explains it, right? And we have the way the residual moves itself, right? Or the variance of the residual itself, right? So really, this is just, there are some similarities between the multiple and the simple, right? This time we're isolating the portion of the explanatory variable that doesn't co-move with the other explanatory variables and influences the wage, which is basically saying we want to find the relationship between, say, x1 holding the other explanatory variables constant and wages, right? So this is the gist of what we're doing, and this is one of the main differences between multiple and simple. So now I would like to do, I would like to build a model that essentially states the assumptions first of the simple OLS estimation of the simple model, right? And I want to compare that to the OLS estimation of the multiple linear regression. I want to compare the two because now that I've already brought up some of the pitfalls of the simple and the advantages of the multiple, I think this is worthwhile, right? So yeah, first of all, one of the most pivotal assumptions of the simple OLS regression are that is essentially linear in parameters, right? Which makes it easier to essentially measure, because remember, we want to essentially estimate the fundamental parameters in the model. So if these parameters are linear, it makes it much easier to essentially establish that the OLS estimator is unbiased, right? Because that's what we're doing, assumptions of the unbiased OLS estimate, right? So linear parameters, right? We want to assume that it operates off of random sampling, right? So I need to start writing this better. Random sampling, right, is essentially, random sampling is useful because it has a few unique properties. It essentially states that each observation is independent of one another. So if we essentially take a random sample from a population of data, right, each observation I'll make is independent of each other, which means they don't influence each other, right? And also each observation operates off of the same probability density functions. So the same probability density function for each observation, right? So random sampling, we have mean independence. So just as I had stated before, essentially means that the expected value of the unobservables given the explanatory variables is zero, right? The zero conditional mean assumption, right? So this is, I've already explained why this is important. It's useful to essentially build a line that goes a line that normalizes the distribution of the unobservables and centers and whatnot. And so lastly, one of the last assumptions is we need a variance that's not equal to zero, because if we have a variance that is equal to zero, when I'd written it out before, it would essentially collapse the unbiasedness of the OLS estimator, right? So these are some of the properties that we're working with, right? So now that we've established these assumptions, it's useful for us to actually derive essentially what the true population parameter for our OLS estimation of beta 1 is, right? Because essentially what we want to do is we want to make sure that if we do a bunch of random samples, will that population parameter, will that fundamental parameter eventually converge to some unique number or some set in stone number, right? And it does, and that's what I'm going to show you right now. So essentially we want to derive the expected value of our OLS estimator to make sure that it converges to some set in stone parameter, right? Which in this case is the true population parameter of the slope, right? So essentially, in order to do that, we need to decompose the formula for the OLS estimation itself, and then go from there, right? So so I derived, so and variance here, right? So essentially we want to decompose this into three other terms, in which the yi, as I've established before, is just equal to beta naught plus beta 1 xi plus u, right? So that's yi, right? But essentially that just means that it's equal to and then also we need to account for the error term, which will get So essentially, we've decomposed our OLS estimator into 3 terms: one with beta naught, one with beta 1 xi, and then one with the error term, right? So, yeah, so I'm gonna erase all this and then come back. So essentially, we're just left with the expected value of all of this, plus the expected value of all of this, plus the expected value of all of this, right? So I put a SSTX over here because essentially, remember when we had the xi minus x bar square thing, the variance of x thing, right? That's essentially represents the total deviations of xi from its sample mean, right? So essentially, that's just the same as the sum of the squares, sum of the total deviations of x, right? So now, if we decompose this, right, essentially we could come to the conclusion that expected value of xi minus x bar, right, is actually 0, right? So since this part is 0, you would essentially just not even look at this equation, right? But if we look at this right now, right, the xi, the beta 1 could be moved over here, right? So let's move the beta 1 over here, and let's cross this out, and then so we just left with xi minus x bar times xi, which is essentially just xi minus x bar squared, which is essentially just SST of x, right? So we have SST of x over SST of x, which is 1. So essentially this whole part's canceled out, and you're just left with the beta 1, right? So let's just write the beta 1 over here. And then, so we have over here, we have expected value of this, right? So we have xi minus x bar over SST of x and ui, right? Which is essentially just moved down, right? So yeah, we want to essentially account for this UI, right? So we're going to take the expected value of this whole thing, right? And essentially, if we move the beta 1 to the outside, move beta 1 to, and just evaluate this part, equals the expected value of xi minus x bar over SST of x times ui, right? And we essentially are left with this, right? We could actually move this part to the outside too. So we just get beta 1 plus this part is moved to the outside, and then we have just the expected value of the unobservables left, right? So if we move this to the outside, so it's just that times the expected value of unobservables, right, plus beta 1, right? We already said that the expected value of the unobservables was actually 0, right? That was one of our fundamental assumptions of the model, right? So we have 0 times this, which was moved to the outside, which is 0. So essentially, the expected value of beta 1 hat, our OLS estimation, is just equal to beta 1, the truth. All right, so I just proved to you that the expected value of beta 1 hat converges to beta 1, which I've said a couple minutes ago. And so yeah, now we're going to move on to our multiple regression model. Okay, so now we're going to go over some assumptions of the unbiased multiple linear regression estimator, right? So we want to establish unbiasedness for the multiple, right? And there's some similarities between the multiple and the simple. We still assume linear parameters, we still assume random sampling. However, because we have more than one explanatory variable, we need to make a couple more assumptions. One, in the sense that there cannot be what's called perfect collinearity. So perfect collinearity is when we have, for example, 2 explanatory variables, right? And essentially we can make linear predictions of one variable and another, right? So there's a perfect linearity between two variables, right? This is incredibly harmful to the reliability, right, of the estimator, and it makes it no longer unbiased because we can no longer take the effect of one explanatory variable on our dependent variable, controlling for other variables. You cannot do that anymore, right? So we need to have no perfect collinearity because it's harmful to the estimator, right? And we also, we have the zero conditional mean assumption, meaning that the unobservables, the average unobservables is consistent across the explanatory variables, right? We still have that, and so from there, as long as we have these assumptions, we can establish whether or not the estimator is unbiased. So let's do that. So we would like to establish the unbiasedness of the multiple regression model, right, by checking for something that's called omitted variable bias, right? So essentially what I mean by that is, are there any factors, right, that are omitted from the model, right, that aren't accounted for, that affect our dependent variable or potentially other explanatory variables, right? So the way we check for that is we want to compare essentially the relationship between our explanatory variable, right, and another explanatory variable, right? Because there are multiple explanatory variables, right? So that essentially is encapsulated by this delta 1 parameter, right? And we want to compare that as well as the true effect of beta 2, the true effect of x2 on y, which is represented by this, right? So essentially what we do is we take the expected value of one of our fundamental parameters, right? And basically this is what it comes out to be, right? We take expected value of this whole thing, right? And this just comes out to be beta 1, and I proved that a couple minutes ago. And essentially we have beta 1, and then this is also beta 2, which I also proved, and we have delta 1, right? So essentially the extent of omitted variable bias is, like I said, these two parameters, right? So these two parameters, right? So, okay. So essentially, if beta 1, if this beta 1, right, is delineating the true relationship of first explanatory variable on wages, right? Essentially what we want to do is we want to see how this group of characters, right, how this group of characters influences the model. So this is the extent of the omitted variable bias, right? So essentially we want to figure out if this is positive or this is negative, or if these are both negative, how does that influence our beta 1 parameter, right? Particularly if this is, for example, if this is negative and this is positive, then this whole thing comes out to be negative, and that effectively pulls down on our beta 1, right, that we want. So, or it could be positive and it brings it up. You know, these are things to take into account, but essentially we want to measure the effect of this number, and if it's significant enough, then essentially we will include the variable. If it's not, then we won't include the variable, right? So this is the extent to which we should include beta 2, right? So that's one thing to take into account. And also, if essentially, given the standards of them, like we just check for omitted variable bias, right? But now, right, we could essentially check for the other assumptions of the model, right, which were linearity and parameters, random sampling, via how we go about the model itself. So how we go about the model itself should be enough to prove it, right? And also, you know, things like no perfect collinearity. But I mean, that's in practice, perfect collinearity doesn't really happen. So I think as long as this number is not significant enough, we should be in the clear in terms of establishing the unbiasedness of the multiple OLS regression models. So yeah, okay, so essentially now we want to look at the variance of a simple OLS estimator and then compare it to a multi. Now that we've looked at sort of other properties. So essentially what we're doing is we are taking the variance of our OLS estimator, right? It's taking the variance of our OLS estimator, right? Which basically means we're essentially examining the dispersion, right, of the OLS estimator from the truth, right? We're taking the dispersion from the truth, and we're asking, what does that look like? What is that composed of? And once we know it's composed of, we could find things that could either mitigate or promote a higher variance, right? And so we need to make some assumptions, right? We need to make some more assumptions. One of them is considered to be what's called homoscedasticity, which basically means that the variance of an unobservable is consistent across different groups or different explanatory variables, right? Which is just equal to the variance, right? So it's relatively unaffected, it's independent, right? And we also need to establish another couple ones. All right, so if we take a conditional expectation of the squared unobservables, conditional expectation of the squared unobservables, right? That should be consistent across explanatory variables. And it should essentially equate to a constant variance, right? So these are sort of our fundamental assumptions that we use to examine the variance of an OLS estimator. And now we're going to actually calculate. So let's get to that. We want to find the variance of our OLS estimator given X, right? So if we want to do that, essentially we've already computed much of this because we established the unbiasedness of the OLS estimator itself, right? So this came out to be beta 1 plus xi minus x bar over SST of x. It's supposed to be like this, and times ui, right? So if we just take the variance of that, right? We could essentially establish the variance, right? So according to variance properties, and according to specifically the scaling and shifting property, we don't really need the beta 1, so the beta 1 goes away. And if we have the variance of xi minus x bar over SST x, right, times ui, we could essentially move this to the outside to just establish the variance of the unobservable to make it a little bit simpler. So we move that to the outside. Variance of ui. But according to our fundamental assumption, variance of the unobservables is it's consistent according to homoscedasticity, right? So it's just the variance, right? And if we could delineate this to be some sort of number, let's just call it q. Let's call it q squared I, and it needs to be squared as a variance property as well. Sorry, q squared I. So q squared I variance. So it's q squared I variance. We'll derive the variance, and we could extrapolate q squared I times the variance to be, well, this is just xi minus x bar over SST of x. So it's essentially just xi minus x bar over SST of x. Square both of them, right? Times the variance. Square both of them, and then times the variance. And essentially, if SST of x is just xi minus x bar squared, right? And we're squaring that again, given the square over here. So we're squaring, this is xi minus x bar squared, like that's SST, and then we're squaring again. So we have xi minus x bar squared, right? Essentially, you would be left with just here. You just be left with 1 xi minus x bar squared, right? But really, this is just this is just after we cancel out everything, this is just 1 over SST of x, right? So if we have 1 over SST of x times the variance, we have just the variance over SST of x. That's what variance over our OLS estimator comes out to be, variance over SST of x, right? So essentially what a good interpretation of this would be the variance of our OLS estimator, right? The variance of our OLS estimator comes essentially from noise from our unobservables, right? It's sort of thrown our reliability is thrown off track because of the noise from the unobservables, right? Right? So as noise goes up, right, the variance goes up. There's a bigger dispersion, right, from its true parameter, right, and which is scaled by the sum of the squares total of x, which are unobservable, right? So if the unobservables goes up, it brings the variance down, right? It's more dispersed. But if if our observables go up, the variance goes down. If our unobservables goes up, then the variance goes up, right? So essentially, to take a step further, we can estimate some of our unobservables to get a more clear-cut delineation of the dispersion of the OLS estimator from its true parameter, right? And that's what we're going to do now. We're going to estimate the variance, and it should be pretty simple because another one of, at the end of the day, we're just leveraging our assumptions. That's all we're doing here. We're leveraging our assumptions, right? About 12 minutes ago, I said this, right? So we can estimate our variance, right, by just taking the expected value of the unobservable squared. So that's what we're going to do, right? So if we take the expected value of our unobservable squared, right, it's essentially the average of our unobservables, right? And that would essentially lead us to get the sum of the squared residuals, because our unobservable squared is just the sum of the squared residuals, our estimated sum of the squared residuals, right? But considering the fact that we need to account for our other fundamental parameters of our model, that effectively delineates a degree of freedom of 2, right? So this gives us a more clear-cut estimation of the variance of our OLS estimator, right? More clear-cut estimation, right? That better delineates the estimation. Now that we've established the variance of our OLS estimator, let's get over to a multiple, and then we'll compare the two, okay? Because there's some important distinctions to be made between the two properties, right? So let's go do that now. Okay, so we want to find the variance of our multiple linear regression model in OLS. So the variance of beta j hat, right? Our estimated beta j is essentially equal to it's essentially equal to this. I brought up some this formula in the beginning of the video when I said like this was the OLS estimator of beta j hat. That's this, except I replaced it yi with ui because we're gonna do a neat little trick with it, and yi is actually a linear function of the unobservables, and we're gonna recover the unobservables. So essentially what we would do, one way to do this is we could essentially shift the denominator to the left. So if we do 1 Rij squared, and then we square it again as a variance property, because at the end of the day we want to just get the variance of ui, right? That's sort of that's part of our objective. So we're essentially decomposing this into the numerator and the numerator, and we're separating out the denominator in terms of this, right? So okay, so this comes out to be r squared j, right? And then we take the variance of ui, right? Variance of ui. So we've separated this to the left, this to the left. Now we just have a variance of ui, which is just variance, right? And but we take this over this, right? This is the squared r squared ij over times 1 over I squared j squared, right? So this cancels out, and then you're just left with variance over Rij exclusion, right? We've proven that essentially the OLS estimators of both the simple and the multiple, right? The OLS estimators converge to some distinct value, right? And I've proven to you why and what are some of the other properties that go into it, and what are the things you need to hold, et cetera, right? But if you learned anything from my incoherent babble, it's that essentially, right, the simple model, it promotes a clear-cut or a more cookie-cutter model, but it's probably missing out on a lot of other variables. So it promotes what's called omitted variable bias, right? But on the other hand, right, when we essentially establish those confounding factors in a multiple regression model, right, and we put those in, it's generally better for unbiasedness, but we don't want to put too many in. We want to keep doing the unbiased estimator test that I showed you before. We're going to keep doing that, because if we put too many in, then we put irrelevant factors that artificially inflates our R squared and whatnot, and it sort of collapsed our no perfect multicollinearity assumption that is required for the variance. So it collapses the reliability of the variance, right, potentially for the multiple regression estimator, right? But at the same time, I'd say it's generally better for unbiasedness, right? So with that being said, the OLS estimator overall, right, we're talking in general, given the simple and the multiple linear regression, right? It's a great estimator. It's consistent, right? It's consistent across models. Its variance is you know, like I said, there's certain things that could screw with it, but its variance is relatively consistent, and it's probably one of the best estimators in terms of linearly speaking, in terms of linear models. So that's all I want to talk about for today, and yeah, thanks for watching.